Now let's look at vector fields in R3, continuing the theme of important and symmetric examples. Um, well, I want a name for the radial coordinate in R3, and in Stewart's book we use rho for spherical coordinates, but in this situation it's actually more natural to use r. So here r is going to be the distance from the origin still, but now it's in 3 dimensions, so it's square root of x squared plus y squared plus z squared. So the first example, just like is exact analog of the first example in 2 dimensions, is the radial vector field again. We just have the components of the vector field equal the coordinates of the point. So that's going to be something that's always pointing outward, and its magnitude, I have that right down here, the magnitude of the vector field is just the distance of that point from the origin. Another way to say it, let me put this into the dynamic viewer here. Another way to say it is that, maybe a little bigger, we're going to take the vector, let me see if I can get this right, the vector connecting the origin to the point of evaluation, and then just take that vector and place it with its tail at the point. Now these are scaled down a little bit, so it doesn't look quite like that, but you can see it's going outward. Here they're not arrowheads, they're little circles, I'm not sure why, just the way this plotter works in 3D. And you can see as we rotate it around, the ones close to the origin are small, and the ones going that are further from the origin are big. The ones outside here, the arrowheads have gotten cut off, so they don't look quite as big as they really are. This is a good example of how, if you're going to visualize vector fields in 3D using a computer, a static picture is incredibly confusing, because if I just did that, it's just really hard to tell what's going on. But if you look at it dynamically, you can get a better sense of what's going on. Some views look really special, because the way the grid works, you're kind of looking down the columns of grid points, but there's nothing really special about any particular coordinate direction here. So if you think that's special, then that's just an artifact of the plotting method. Okay, so again, you can think of it as the flow of a fluid. It's not just it doesn't just have a source at the origin, and we'll figure this out much more explicitly. But I claim it's really, again, something that's appearing everywhere, because the flow gets stronger and stronger as you go out instead of weaker. So it can't just be coming out of the origin. So you could visualize this as like you've got some sort of foam, like styrofoam, permeating all of space. It's all on fire and generating smoke, and that smoke is kind of billowing out and being created everywhere. It's a little bit hard to think of that, but that's not a horrible model. It's not a very realistic force field because it gets bigger as you go out. So not the best one to think of there. We talked about how the magnitude of it is just the radial coordinate. And again, it's continuous, differentiable, linear. I mean, you can't get much of a nicer formula than x comma y comma z. Okay, so what about the unit version of that? We can divide that by its magnitude, and we get something that isn't terribly interesting, but is a good way station on the way to the more interesting one. And that's just, again, radially outward, unit length everywhere. So really easy to visualize, although, again, it takes a computer to actually get a good picture of this, because they are hard to do by hand. So, again, discontinuous to the origin. It flips from left to right, or wherever direction you're going as it goes to the origin, it flips to its opposite. But it's a unit magnitude, and it's bounded everywhere. So G3, that's a really interesting one. This is where we take r, the radial vector field, and here I claim the appropriate thing to do is divide it by r cubed. And we'll see why r cubed here and r squared before. Well, there's an obvious link to the dimension, but why? Why do we do that? I think we want to postpone the deep reasons for that. But the claim is that this is an incredibly important, famous vector field. This is the Coulomb field from a point source at the origin, point charge at the origin. Or it's, if you put a negative on it, it's gravity. So let's fit to the window. And again, you got to kind of look at it and rotate it around. Hopefully you can see that the arrows are bigger inside. They're getting smaller out here, and they're bigger in here. And so we've got something that's always pointing radially again, and pointing away, because I'm using the repulsive version. We could negate it to get an attractive one. Oh, here we're looking down the lines, just the grid that they use to evaluate, which kind of makes it look a little simpler, but still kind of misleading. And they get infinitely long as you go towards the origin. So you can hopefully believe me that this is a good vector field by looking at the magnitude. The magnitude of this vector field is going to be the magnitude of what you started with, which is just little r, and divided by r cubed, so the magnitude is going to be 1 over r squared. there's that inverse square law that's the famous about gravity and electrostatics. And so that's some justification as to why this would be such a good thing to do and divide by exactly this factor. Mathematically, we're going to see some very beautiful reasons why we would do that. You can also think of it, an equally good reason to think about this guy, is it's the flow of a point source at the origin. My claim is that that's really exactly something that's coming out of the origin. Let's look at 3D rotate again. And you can get some justification for that by noticing that the flow is going to be stronger near the source, and then it's going to dissipate, and it has to fill out more space as you go, and it's going to get weaker as you go. And exactly that correspondence of as you go out, how much does it have to weaken to sort of conserve the material that's flowing and not have it created or destroyed at any other point but the point source of the origin. That's going to be a really good justification for the 1 over r squared nature, or equivalently dividing by r cubed. But that's getting a little ahead of ourselves. It's a really good example. Okay, oh, and then of course that's definitely discontinuous. It actually blows up to infinity at the origin, just like the G2. And that's a little disturbing, but that's partly an artifact that point sources are a little bit of unrealistic. They're certainly unrealistic in gravity. They're not incredibly unrealistic in electrostatics, though. Like an electron or proton is pretty darn close to a point source, especially an electron. Okay, so what about this guy? It looks like I've just accidentally copied. I actually did copy and paste the vortex vector field formula from the 2D case to the 3D case. And you might be wondering, where's the K? Where's the Z? What happened? Is that what you really mean? In fact, that's exactly what I mean. That if you look at vortex, if you look at rotation in 3 dimensions, a rotation has to have an axis in 3 dimensions. You can't rotate uniformly around a point. Think about that for a little bit. You have to have an axis for rotation. So what I'm doing is I'm taking the vortex vector field, I'm basically adding plus 0k. Hello. I'm not sure why that's not bolding it. It's supposed to be bold. For some reason it's not bolding it. I'm not sure why. So it's putting 0 times k in here, and it's refusing to use the z variable in here. What that does, and it's a very standard thing to take a planar vector field and promote it to 3 dimensions, is it just means that because it doesn't depend on z, it will be the same in every horizontal slice, and because it doesn't have a k, it won't ever point in the vertical direction. So I'm just copying and pasting, basically, a bunch of copies of this vector field. And here I'm looking at it down the z-axis, and you can see all those copies kind of stacked up on each other. I'm copying and pasting a bunch of copies of the vortex vector field that's getting stronger as you go in. So it's the same on all horizontal slices. So now we're looking on the horizontal z equals constant slices. And you can kind of see the swirls, swirls, swirls. Here we're looking edge-on, so it's hard to tell. Okay, so it's just this swirly pattern copied and pasted uniformly for all values of z. And that's a really important trick for promoting a 2D vector field to a 3D vector field. And that's really the right analog of the vortex in 2 dimensions, because there's no way we can make it uniformly swirl in a 3rd dimension. It just doesn't work. It's a fundamental thing about rotations. And so this guy, well, I mentioned that in 2 dimensions we could think of it as a slice of the magnetic field of a wire. Well, here, this really is, honest to God, the whole magnetic field of a wire. So a wire going along the z-axis is going to have this magnetic field. Stronger toward the middle, swirling around, and getting weaker as you go out. And we'll justify further why that's exactly the right magnetic field. Or it could be a whirling fluid. It's not exactly a vortex like a whirlpool draining down into a drain, because it is uniform top to bottom for any value of c. But it's a uniform whirling around a line that gets stronger as you go in. Okay, and otherwise it has a lot of the same kind of properties of the 2D vortex. So that concludes our tour of the most important highly symmetric vector fields in 2 and 3 dimensions.